All right, homework problem number 1. We're doing a 3.5 G pull-up. So you're given a formula for CMQ. You should get minus 5.026 radian. CLQ is 0, so those are those extra values we need when the airplane's pitching. This is how the lift and pitching moment change. Then the mass ratio. Should be getting that. And the trim lift coefficient, which is CW, is 0.3801. Okay, make sure you show your work. Meaning the numbers substituted in the formulas and that you did the calculation. The delta E is a long formula. So I'm going to give you the intermediate answers. CW goes here, and then there's the stuff in the brackets. Should get that. And the stuff in the parentheses. These are the two parts that get multiplied together. So you need 9.88 degrees of elevator per G. Oh, that's multiplied. Sorry, that's multiplied by 3.5 minus 1. So I multiply both sides by this thing here. So that's quite a bit of elevator. You need almost 10 degrees. Yeah, hang on. You almost need 10 degrees of elevator to do that pull-up extra. Yeah. Oh, this thing here includes the determinant here. Oh, and the determinant, just double check that. Should be that. Yeah, so that's everything that multiplies CW divided into the two parts. There's the parentheses and then the bracket stuff divided by the determinant. I was just trying to give you some intermediate answers. Watching those, did you do it that way? Yeah. Yeah, so that should get you going on that. So that's really just plug and crank. And then again, show your work. So make sure you show the work that goes up to this. All the numbers plugged into the formula. Let me see if there's any questions on Zoom. Nope. And then your spreadsheet should show this value on it for delta E. And did I ask you, I did a column for CL trim just as an intermediate answer for this thing here. Did I ask you to put that on the spreadsheet? I forget. Because this changes with airspeed. So that's why I just did it as an intermediate answer column on the spreadsheet. Okay, make sure you submit a printout of your spreadsheet with the scanned in copy and also submit the actual Excel spreadsheet to Blackboard. So 2 different files, right? Great. I need your PDF, which is your scanned stuff, and then I need the Excel spreadsheet. Yeah, so 2 different files. Oh, is it okay if we expand? Oh yeah, add it to columns on that one, sure, that's fine. In other words, the previous homework, you did a spreadsheet with these airspeeds. You can just add a column on that if you want. But make sure you turn that in again. Okay, problem number 2. What we're doing here is we're getting ready to add a vertical tail. And we'll start talking about the vertical tail and yaw stability a little bit today. But the preliminaries we need for that is we need to know, well, where is the aerodynamic center and what is the lift curve slope of this thing so that we can predict the lift of it. Now, the lift of the vertical tail acts sideways due to a side slip, but it's still an aerodynamic surface. So we calculate all of that stuff as if it's just a wing. And because a finite wing has downwash coming around the wingtips, we're going to get flow around the top edge from one side to the other, just like we did with a finite wing. But because the fuselage is here where I do this black thing, it tends to block the flow of the bottom part of the vertical tail. You don't get very much flow around that end. And there's various ways to approximate that blockage. And the way we do it is we just pretend that the wing has another part like that so that you don't get flow around this end. So it's just an approximation of calculating the lift curve slope and eliminating this flow at this end that doesn't happen. So only for this problem are we going to use twice the fin area. So the area of the fin is FS, or SF, and we're going to use twice this to calculate the aspect ratio and the lift curve slope. But then for everything else, we're just going to use the top part because that's all that's really there. Make sense? So that's what that wording is about that. All right, so the stuff you need for this. So the wingspan, there's my picture. Oh, here it is. Yeah, this distance is 12 feet. But for the fictitious wing, the wingspan is going to be double that. So B over 2 for our calculations is going to be 12. Is that half? And then lambda, you should get 0.625. And then the formula for C bar, that's the mean aerodynamic chord. So that's the average chord somewhere in here of this wing. And then use the big formula. To get the curve flow. And it's A of F. F stands for fin. Just like we had A for the wing and AT for the tail. And let's see. I told you to use little k of 1. Beta is 1. Big K is 1. Again, we're going to use twice the half area of this thing. So we calculate that with the formula of the average of the tip and the root chord times B. So you should get 156. All right, so it's the average of this thing and this thing times the whole distance there. Because that's what we're going to use to calculate our aspect ratio. And then you need the tangent of the C over 2 for the lift curve slope formula, so you should get 0.125. And then A sub F from the big formula You should get that. And again, nothing in here is new. We did that for the wing and the horizontal tail. So we're just doing it for another flying surface that's the vertical tail. So you guys can do this in your sleep now, right? Maybe that's a bad thing. You wake up in the middle of the night thinking about this. And then you go, just like we did for the wing and the horizontal tail, we're going to calculate y bar, which is actually the location in the z direction of the aerodynamic center, because we want to know where does the lift act. And so that's the formula for the appendix, right? The chart, and you use uniform CL alpha. Let's see. This turns out to be 5.539 feet. So that tells us the lift of now just the top part acts here, which is what's really happening. And then how far back does it act from the apex? That's X bar. And that's where you use the formula where you need the tangent of the quarter chord line, because it's subsonic. So you should get 0.1875 for that. Stick that into this formula along with your Y bar formula to get the value. And again, all that stuff we've done twice already. We did it for the wing, and then we did it for the horizontal tail. So again, show your work, show calculations for all of this. And then this is going to tell us, now that we know, let me get a different color. Now that we know on the vertical tail, we know this distance here and this distance here. Then on the figure, we know the distance here, I forget what it is, far back it is from the CG, and then that's our moment arm for the force generated by the vertical tail. And in fact, it's on the diagram, but you don't really need this information until the next homework set. But really, this vertical tail sits on top of the wing. Remember, the canard is like up here, and the wing actually sits like there, with the vertical tail sticking up from the back end of the wing. Sometimes canards, airplanes are built where the vertical tail is actually on the tips of the wings sticking up. Let's see, we need to finish our example for the four-place airplane. We were doing control force per G, and so we found out there's a thing called the maneuver point, stick free. And we had formula for calculating that location, so that's what I want to do is run through the numbers for that. We didn't get to that last time, right? We did. Did we calculate the location of HM prime? We did that last time? We had that big long formula for HM prime minus HM, right? Yeah, so that's what I want to do is put numbers in. I was trying to remember if we'd gotten to that or not. Sorry, I forgot to turn my phone to silent. So we're flying at 220 feet per second, 5,000 feet. And the data we need is the hinge moment information. So this is the hinge moment information we have for this airplane. We used this before. There's the Q part that's added on, and then here's CLQ, CL delta E, CL alpha. This is all this, just the normal stuff we've calculated already for this. The determinant for this is minus 4.76. And then we've already calculated HM minus HN. So that's the location of the stick fixed maneuver point relative to the neutral point. And now we want to calculate HM prime. So we did all this before. All this is from before. The first thing we have to calculate is A prime. So get out your calculators and punch that. You should have the CL alphas here, CL delta E's there, CHE alpha is here, CHE delta E is up here. Somebody's asking for clarification. This is CL sub delta E there. All right, so you should get number for that. We're getting did you get that? All right, and now we have to stick that into the big formula. And so that's going to give us the distance from the maneuver point to the stick-free maneuver point. And I'll draw it on there once we get a number here. And the other points that we've already calculated were the neutral point and the CG is up here. We've calculated all those. We calculate the neutral point. We know where the CG is, and the maneuver point we did before. So now we're trying to find out where this is relative to that. So you got numbers for that? It's not hard because this is 0, right? So that's negative, so it means that HM prime is smaller than HM, so it's actually in front of. So let's say it's here. And in fact, we can find it exactly where it's located because we know some other distances. We know these other distances, so HM prime minus HN is, in other words, we're going to find out where it is relative to the neutral point, is HM prime minus HM plus HM minus HN. I just added and subtracted HM. And this is what we calculated here. And then we knew this from before. This is how we figured out that the maneuver point was behind the neutral point. So where is the maneuver point relative to the neutral point? So that's a negative, so it's in front. So the maneuver point H M prime, I guess I already drew it down there, but let's get it up there. So obviously we need to make sure the CG is in front of that thing. So as you might be getting the idea, every time we add something to the airplane or we add a new maneuver, we have another point that we have to check out to make sure that the airplane is stable or gives the proper feedback. Yeah. Yeah, and if you remember, the stick-free neutral point was further forward than the stick-fixed neutral point. So you just have to calculate all of them and make sure your CG is far enough in front. So let's say we add flaps to the airplane. When the flaps are deflected, we need to recalculate CM alpha and the neutral point, because it could change by deploying the flaps. Say you have leading edge slats, same thing. So anything you add, if you have a fighter aircraft and you add missiles, you have to do it again. Make sure the airplane's still stable. If you have external fuel tanks, same thing. So you have to check all those out. The engine of the propulsion, we included those values CMP 0 plus the change in CMP with respect to alpha times alpha, and we pretty much up to this point to simplify things have said, well, the engine doesn't really affect the stability or the airplane much, other than just providing thrust. But in reality, you have to look at, well, how does that change the pitching moment? So you have to look at the propulsion effects and even structural flexibility. Let me draw a picture of what I mean by that. So this is an extreme case, but so this is, I'm going to draw a picture of an airplane, and this is in cruise. So here's our airplane, and for some reason we decided to make a real long tail boom back to the horizontal tail. Like that. Okay, right? And let's say that a gust comes along. Vertical gust. And so it's going to push up on the wing, but it's also going to push up on the horizontal tail. And let's say this tail is so floppy that the tail goes like this. Now this is obviously exaggerated, right? But that gust is not only going to change the pitching moment, but that thing's going to flex, and that's going to change the pitching moment as well, right? So we have to analyze structural dynamics in response to the alpha gust. Or weird things can happen when you deflect the elevator. So that's with the gust. Let me go over to the other board. Let's say we deflect the elevator upwards to trim. Here's our airplane. And we've deflected the elevator up like that, which pushes down the tail and causes it to flop downward. You wanted the airplane to pitch nose up when you do this kind of deflection, but because the structure deflects down, we might actually get more of a nose down pitching moment. In fact, the elevator there is kind of acting like a trim tab, right? It's making the structure flex and flop, and that changes. And so you could actually get control reversal. What you want here is nose up, but you get, because this thing flops down, you get a forced nose down. Now this isn't very common with the fuselage because usually it's beefed up and strong enough, but you could see it could happen, right? But often the wings can be long and thin, and the ailerons are outboard on the wings, and if you're not careful with the structure of the wing, when you deflect the ailerons, it can twist the wing and cause the exact opposite effect of the aileron deflection. So you can get control reversal there. And obviously, it's really hard to fly an airplane where the controls operate opposite of what you think they should. Yeah, so we deflected this thing to get nose up, right? Because it's going to push the tail down, which pushes the nose up. Yeah, so what you actually get is nose down, sorry. Have I brought this foam airplane in before? Did we bring it in when we talked about orientation of the airplane? Nope. Anyway, we're going to switch now from doing what's called longitudinal flight to lateral directional flight. And so this airplane makes it easy. So longitudinal flight is forward and up and down and pitch. So forward velocity is u, vertical velocity is w, which is related to angle of attack, and then the pitch is the pitch angle theta, or the pitch rate q. And then the controls for this motion are throttle and elevator. Elevator pitches the airplane and controls the angle of attack, which gives you the lift and the drag, and then thrust counteracts drag. So we're talking about motion forward. Use a different camera angle here. Yeah, there we go. So we're talking motion forward, motion up and down, And notice all that motion is in in a vertical plane, right? Imagine a plane going across and up and down. Now, I don't mean an airplane, I mean a mathematical plane, right? So this is in that plane, this is in that plane, and then the rotation all stays within that plane. So that would be the XZ plane. Lateral directional flight. So that's longitudinal. How well does that show up on Zoom? Really crappy, probably. And then it's roll and yaw. So roll rate is P, and also psi is the heading angle, and then the bank angle. So it's just the other three directions of motion. The other velocity, we have U and V, U and W. So the third velocity is V. And then as far as angles, we have pitch angle here, and over here we have the other two angles. Yeah. That one? Psi? Guess it's kind of like a trident. And so this motion is the airplane sliding sideways, so that would be going like toward that direction. And then roll is like this. And then yaw is like this. And the variable that we tend to derive from this is we derive a side slip angle beta from the side velocity. And beta is equal to the inverse sine of the side velocity divided by the total velocity. Just like alpha comes from U and W. So as a reminder, positive side slip is coming in from the right side of the airplane. So if we have a top view, here's our airplane. Relative wind's coming in like this. This is the angle beta. So lateral directional flight compared to longitudinal is both easier and harder. So which do you want to hear first, the good news or the bad news? Anybody have a preference? You want to hear the bad news? So for longitudinal flight, roll and yaw are coupled, meaning you can't consider them independently. On the longitudinal, we just had pitch and that was it. But on lateral, it's over here. Roll, yaw are coupled. Not on this side. And we had pitch only here. So what I mean by that is that if the airplane starts to roll like this, partially because of the vertical tail, air pushes on the vertical tail, and it will cause the airplane to yaw as well. So a roll can lead to a yaw, and vice versa. A yawing motion, force on the tail, it's above, will cause the airplane to roll. So you get both at the same time. And in fact, that's part of what happens when you get into a spin, is it's yawing and rolling, and all of it's coupled together. So that's the bad news. How about the good news? This is the part. Over here on the longitude trim, an alpha to trim. So how about over here? Trim beta, because that's our angle of our air coming in, just like alpha. And how about aileron to trim and rudder to trim? Because those are the control surfaces. Symmetrical, so there's nothing that's going to cause it to roll one way or the other, so the ailerons are 0. And the same thing with the rudder. The rudder's 0 for cruise flight. So that makes it easier. Is for cruise flight, beta is 0, aileron is 0. So there's no real trim condition. And it's because the airplane's symmetrical and the airflow is symmetrical. So how about longitudinal? Why did we need pitch trim? We just point the nose so the airflow goes straight over the wing and everything, and we get no lift. Oh, that's a problem. So that's the only reason we need pitch trim, is because we have to have unsymmetrical airflow to get the lift because there's weight. So if we're in outer space with our airplane, there is no pitch trim. Of course, there's no air either, right? So we'll spend time talking more about the stability on the lateral directional side, because the trim problem is not that big of a deal. We'll continue that on Friday. We have a quiz. Make sure you wrap up your homework and get it turned in. And we're done for today.
Dr. Stack,